So this is definitely a U-sub problem. We want to figure out which function would be the derivative of which function. We have to assign a U and we have to assign a du. So this part right here in parentheses looks pretty familiar. I think we can identify that this is the derivative of one of the trig functions. So let's write off to the side of the page. Let's say that we know that the derivative of secant of x is secant of x times tangent of x. And that the derivative of, forgot the derivative identifier. And then the derivative of cosecant of x is going to be negative cosecant of x cotangent of x. So it looks like we're going to be using this one on the bottom. We have exactly the derivative of cosecant. And what's more, we have cosecant itself, which is pretty useful. We have cosecant to the second power. So we want to just set cosecant to the first power to be our u. So u would just be cosecant of x. And then du, of course, would be negative cosecant of x times cotangent of x dx. So let's go ahead and start substituting things in. Integral 3 pi over 4 to 5 pi over 6. So we're going to have u squared times du. And this is really similar to the ones we've been doing in class so far in the way that the calculus isn't hard. The thing that's really hard is understanding how to approach it, understanding what should be u, what should be du, and how to set things up so that we actually can integrate. But once we get it into a form like this, it gets much, much easier. So we're going to add 1 to the exponent. We're going to make it u to the third power, but then of course we also have to divide by a 3. So let's go ahead and make this 1/3. Oh, and as soon as we take the antiderivative, we don't have the integral symbol anymore, so it's going to be just brackets. So we have 1/3 u cubed, and then u is cosecant of x. So let's just substitute that back in. And then this is a definite integral. So we're definitely going to be plugging in our endpoints. Clear up a little bit of space. So we want to plug in the top endpoint into the function. We're going to have cosecant cubed of 5 pi over 6 minus cosecant cubed, not cosine, cosecant cubed, 3 pi over 4. So let's ask ourselves, what is the cosecant of 5 pi over 6? So we're going to need our unit circle. So we have 5 pi over 6 is right here. That's a 30, 60, 90 triangle. The x is negative, but the y is positive. So if the sine of this angle is positive 1/2, then the cosecant of this angle is going to have to be 2. So that means cosecant of 5 pi over 6 is just 2. We have 1/3. This is going to be 2 to the third power. And then we're going to do the same thing with 3 pi over 4. So 3 pi over 4 looks like this. It's going to be in the same quadrant where x is still going to be negative and y is still going to be a positive. We want to do the same thing. We want to take the sine of this. So if the sine of 3 pi over 4 is positive 1 over square root of 2, that means that the cosecant, which is the reciprocal of sine, is just going to be square root of 2. So we have square root of 2 to the third power. Excuse me for a second. I think I need to disconnect and reconnect my headphones. I'm having a bit of a static issue right now. All right, that seems to have solved the problem. Sorry about that. It's always something. Technology, you can't live with it, can't live without it, though I do try sometimes. I do try to live without it. Doesn't work very well. So back to the problem. So we can easily identify that the 2 to the 3rd power is just going to be an 8. And then we have square root of 2 to the 3rd power. So let's figure out how we can put this into a complete simplified form. So I want to go over here on the side of the page and I want to rewrite it in a slightly different way. We can write it like this. So this is going to make the radical go away in our first factor. So this is just going to end up being 2 times square root of 2. And of course, we have the 1/3 on the outside. So if we decide to distribute the fraction, we would get 8/3 minus 2 square root of 2 over 3. Or you could even put it as just one fraction if you'd like. All right. Not the hardest problem in the world, but setting it up is a bit of a doozy. It takes a bit of thinking to understand how to tackle a problem and how to do it strategically using the methods that we've learned so far. Not always easy, but every time you do it, you get a little bit better. Repetition is key. So today we're going to be finishing off our section on trig integrals, and then we're going to be moving on to another trig-related section of integration. So the things we've been doing so far involve taking an integral and using the trig identities to rewrite it in such a way that it's easy to integrate. The thing that comes after this is going to be something a little bit different called trig substitution. I don't want to spoil the surprise for you guys, so we're going to just finish this up real quick and then we'll get into trig substitution. We have just a few more trig integrals I want us to do. It's good practice, really good practice to do a few more of these problems. Let me find a good one. All right, let's try to integrate tangent cubed of x over cosine to the 4th power of x. So we want to see if there are any trig identities that would help us simplify this quite a bit. Our first thought might be, well, if we can turn it into some kind of a U-substitution where we have one function with a single power and the other function not necessarily being a single power, that would work really, really well. It would make our lives quite a bit easier. But I see a tangent, I see cosine, and I know that they are kind of related. There is one particular identity that connects the two functions together. We know that the tangent of an angle can be written as sine of the angle over cosine. So that means that this is just going to be sine cubed over cosine cubed. So let's go ahead and see if that'll help us. There's no guarantee that it will, but it's a good idea to try it. So instead of tangent, I'm going to write this as sine to the 3rd power on top. And then we have a cosine to the 4th power initially, but we're going to put another cosine to the 3rd right next to it. So altogether, it's actually going to be cosine to the 7th power. And if we just had a single power of cosine, that would be really, or sorry, not cosine. If we had just a single power of sine, that would be really, really nice. But there might be a way to do it. I think maybe the Pythagorean identity may help us out quite a bit. The one that tells us that sine squared x is 1 minus cosine squared of x. So let's go ahead and split this up a little bit. We're going to make it a single power of sine multiplied by a double power of sine, like this. And then we can replace this sine squared of x with 1 minus cosine squared of x. Again, there's no guarantee that it will help us, but it's good to try out all of our options. Good to exhaust all of the things we think might be useful to us in this situation. So what I'm going to do is I'm going to replace this with 1 minus cosine squared, but then I'm going to distribute. So we're going to have sine squared of x, or no, sorry, we're going to have sine of x minus sine times cosine squared of x. So a prevalent theme in this class, and just particularly in the integration section, is that oftentimes things have to get uglier and nastier before we can make them nicer. We had something that looks pretty concise, nice, simple, rational function, and we made it into this long, scary looking thing. And we're trying to determine if that was even necessary or if this is even going to help us at all. But how do we know? How do we look at something like this and know if we did the right thing? Because there are multiple ways of doing this. There are multiple trig identities. We could spend an afternoon just taking all of these different identities and rewriting these things in a different way. But how do we know for sure if it's really going to work or not? How do we know if this is not going to work? Because if it's not going to work, we just want to stop right there and then try a different approach. But how do we know that? So we want to use our knowledge of trig. We want to use our knowledge of algebra, all the things we learned in pre-calc, just to look at something like this and determine if we can do something in this form, do something with an integral that looks like this. So I feel like we could split it up, and that's another prevalent theme of integration in this class. It's always in your best interest to break up a huge problem into small, more manageable problems. It just makes the problem that much easier. So I want to see if we can do something similar to this one. So I see we have a difference of two functions on top of one common denominator. So I'm thinking it may make our lives much easier if we're able to split this up into two fractions. But before we do that, I got to clear up a little bit more room on the board. I'm just making things small because it could potentially get ugly. I want to make sure that we have enough room on the board and I don't have to race and rewrite a bunch of stuff. So let's go ahead and see if we can break it up into two separate integrals. So our first integral is going to be sine of x over cosine to the 7th power of x dx. And then the next integral is going to be minus sine of x times cosine squared of x over the same denominator, cosine to the 7th power of x. So I think this works out pretty nicely, at least for the first one. It is a very basic U-substitution problem. We have a u on the bottom to the 7th power. We have a du on top to the 1st power. Life is good. It's working out really nicely for us. So let's go ahead and set u equal to be cosine to the 7th power. Not cosine to the 7th power, but just cosine. U is cosine of x. Du would be derivative of cosine is negative sine. So we would have negative sine of x dx. But I want to go ahead and move the negative sign to the other side. So it'll be negative du and then positive sine of x. So far, so good, but let's see if we can do something similar with the next one. There is a bit of simplification we have to do before it's even possible. So we have a cosine squared on top. We have a cosine to the 7th power on the bottom. We can use those laws of exponents from Algebra 2 to help us simplify this quite a bit. So we're going to remove the cosine squared on top. We have 2 minus 7 is negative 5, so we're going to be left with 1 over cosine to the 5th power. So we've already done the first one. This is just going to be u to the 7th power over, or under du over u to the 7th. And then this one, we already have a minus sign, but we have another one from the du. They're going to join together and make it positive. So it's going to be plus this second integral, plus the integral of, we have, the sign is going to remain from before. We have, this time we have a sine over cosine to the 5th power of x. Dx. So then we can use the same exact u and the same exact du. So this is going to be u to the 5th on the bottom, and then we're going to have a du on top. And we already took care of the negative sign, so we don't really have to worry about that. Now all we have is the integral of du over u to the 5th power. So let's rewrite this. make this one into u to the negative 7th du, and then we'll make this one into u to the negative 5th du. From here, all we need to do is add 1 to the exponent and then divide by the result. So we would get u to the negative 6th power, and then we're going to divide by negative 6. And then this one is going to be something similar. We're going to add 1 to the power. We're going to get u to the negative 4th, and then we're going to be dividing by negative 4. And then we just want to substitute the u back in and turn these negative exponents positive by taking the reciprocal. So our full solution would be this. It would be minus 1/6 and then 1 over cosine to the 6th power of x. And then we're going to have minus something similar, but it would be minus 1 over 4 times cosine to the 4th power of x plus c. That one was pretty tricky. That one, it took a bit of time to understand what would be useful, and we had to kind of stop every step of the way and just confirm that we're actually doing the right thing, because we know that if we take a method that doesn't work very well and we keep going deeper and deeper, we're just wasting more time, more effort. So it's always a good idea to be able to verify that this is going to help us at all before we go any further. Because if it doesn't help, we just want to stop right there and then choose a different method. Maybe a different identity would help, but it worked out pretty well on this one. We're able to break it up into 2 smaller integrals, which we were then able to solve pretty easily. Not so bad. Let me find another good one for us to do. Let's try this. We have a definite integral. We're going to be taking the definite integral from pi over 6 to pi over 2 of cotangent squared x dx. So I'm going to open up my sheet of trig identities. Give me a quick second. It'd be nice if my computer wanted to cooperate. It doesn't seem to want to cooperate today. So, all right, I have the sheet of trig identities open, and I'm going to see if we can decide on one that would be useful in this situation. So we definitely do need a trig identity. There isn't a simple way to integrate this. We have to simplify and then integrate. We have to make it so that we are able to integrate it. Ideally, we'll turn it into a U-Substitution problem, or maybe an integration by parts problem, or maybe something even much simpler than both of those. So I'm going to go to the table and I'm going to look for cotangent squared, see if that appears anywhere in the trig identities table. And I see it in a few different places. It looks like this is part of one of the Pythagorean identities. So there are a few different ways we can do this. We might try maybe splitting it up into a sine and a cosine. Because if tangent is sine over cosine, then that means cotangent is the reciprocal. That would be cosine over sine of x. And then we just want to square both sides. But before we even go further, before we continue, let's see if this would even be useful to us. So if we didn't have a second power on top, if this were just a single power of cosine of x, life would be much, much simpler. We would have our answer much, much faster. But unfortunately, that's not what we have. We have a second power on top, second power on the bottom, which makes things a bit more complicated, but we can still integrate it. It's still manageable. It just might take a bit more time, a bit more effort. So one thing that kind of pops into my mind whenever I see a sine and a cosine with the same power is to maybe use one of the Pythagorean identities. I think we want to maybe rewrite this cosine on top in terms of sine. That way we don't have 2 different functions, we just have one function, and it makes it a lot more manageable. So I want to see if we can put this in terms of only sine. And in order to do this, we can use the Pythagorean identity. Cosine squared of x is 1 minus sine squared of x. So then our cotangent squared x becomes this. It becomes 1 minus sine squared of x over just another sine squared of x. So far, it looks like it's working out pretty well. I'm happy with this choice. It's proven to be really useful and really helpful. Integral pi over 6 to pi over 2. This is going to be, well, we can simplify it before we even substitute it in. We can make this into two separate integrals. Our first integral is going to be 1 over sine squared of x. And then our second integral is going to be minus sine squared of x over sine squared of x, which is just a fancy way of saying 1. So we have minus essentially just the integral of 1 dx. This one is simple enough, but let's talk about the first one. So we have 1 over sine squared of x. I want to look at the table and then see if there's anything that could help us out with this one. Maybe one of the double angle formulas could be useful to us. Take a quick look, see what we have. So we might be able to use one of the double angle formulas. It isn't guaranteed to work, but we should at least give it a try, exhaust all of our options. The one I am thinking about would be the one that says cosine of 2x is equal to 1 minus 2 times sine squared of x. And let's manipulate this a bit so that it looks more like what we have in the integral. So namely, let's see if we can make this into 1 over sine squared of x. So I think what I want to do first is I want to subtract 1 from both sides. So we would have cosine of 2x minus 1. And then what we have left on the right would be negative 2 sine squared of x. And then from there, we can just divide everything by negative 2. And now on the right, we have sine squared of x. What we really want is we really want it to be cosine. No, sorry, I don't know what I'm saying. We really want it to be 1 over sine squared of x. We want to take the reciprocal. So let's go ahead and take the reciprocal of both sides. All right, so we would have a cosine of 2x on the bottom. And even then, this won't prove to be all that useful. We still have something that's not exactly easy to integrate. So I don't think this is really the right approach at all. I think we don't want to go any deeper in this approach. We don't want to sacrifice any more time doing something that we think won't work. So we want to take another look at the table and see if we have anything that might help us out with this. So I want both of you guys to look at your own tables and maybe type in the chat if you have any recommendations. I'll do the same. So please type in the chat any suggestions you might have for a trig identity that might be useful to us in this situation. Do you guys have any ideas? I was just taking a look at my own table, and I think I found something that might work a little bit better. So instead of using the reciprocal identity or the quotient identity to begin with, I think we should start with the Pythagorean. There is a Pythagorean identity that tells us that 1 plus cotangent of x is equal to cosecant squared of x. And then we just want to subtract both sides by 1, and then replace our cotangent squared of x with this cosecant squared of x minus 1. So we have the integral of pi over 6 to pi over 2. We're going to make this into cosecant squared of x minus 1 dx. And how is this useful? Why is it better to have this instead of cotangent squared of x? So there are a number of reasons. We want to not talk about we don't want to talk about this in terms of the identities. We actually want to bring this into a calculus topic, into a calculus context. We want to think about derivatives. We want to think about integrals. We want to ask ourselves, why is this easier to integrate than this one? Well, it's because I think this happens to be the derivative, or at least part of the derivative, of one of the trig functions. That doesn't apply to the cotangent squared. This isn't really an elementary antiderivative, or sorry, an elementary derivative is what I meant to say, but I think this one definitely is. So we want to think to ourselves, we want to see if there is a function that we can recall that has cosecant squared of x when we take the derivative. Well, the derivative of tangent is secant squared of x, and the derivative of cotangent is going to be negative cosecant squared of x. So yeah, this is going to work out really, really nicely. We have something that we do know how to integrate, but we want to maybe flip the signs on these, because cotangent has a negative cosecant squared as its derivative. What we have here is positive. So let's go ahead and make this negative integral. And then because we turned it positive, we're going to put the 1 first. It's going to be this time a positive 1 and then negative cosecant squared. And from here, we turn it into a much easier and much more simple problem. We can just take it term by term. I'm going to write it maybe up here. So we have negative, the antiderivative of 1 is just x. Antiderivative of cosecant squared of x is just going to be cotangent, as we can see. So we're going to have minus cotangent of x. No, just positive, because the antiderivative of negative cosecant squared of x gets us positive cotangent. So it's going to be plus cotangent of x. And this is a definite integral. We have our limits of integration to plug in at the end. Keep the negative sign. So we're going to plug in the pi over 2 first. We're going to have pi over 2 plus cotangent of pi over 2 minus the same thing we get when we plug in pi over 6. Pi over 6 plus the cotangent of pi over 6. What am I doing today? Why am I writing 5? And I think we can clear out a little bit of space. We don't really need all this stuff anymore. So what is the cotangent of pi over 2? So if we imagine the unit circle here, we don't have to imagine it. I'll do you one better. I'll actually draw one. Won't be very good, but it'll be still useful at least. So we have cotangent of pi over 2. So pi over 2 is going to be one of the coterminal angles. Right? We call it a quadrantal angle because it's an angle formed along one of the quadrants. It's equivalent to 90 degrees. What is the cotangent of pi over 2? Well, if the tangent of pi over 2 is going to be y over x, we have x is 0, y is 1. Tangent would be undefined. We would have 1 over 0. Cotangent, however, would be the reciprocal. So cotangent of this angle would be 0 over 1, meaning that the cotangent is just going to be 0. So we have negative pi over 2 plus basically just 0. And then we have minus pi over 6, and then we have the cotangent of pi over 6, which is going to be this right here. So this is going to be, that the cosine of this would be root 3 over 2, and then the sine of this would be 1/2. Tangent is sine over cosine. Cotangent is cosine over sine. So this is going to be our first coordinate over our second coordinate. So we're going to add 3 pi over 2. And then we can either divide by 1/2 or we can multiply it by the reciprocal of 1/2. We can multiply this by 2. And we don't need the unit circle anymore for this. So we can simplify this quite a bit. The 2 on top cancels with the 2 on the bottom. We're going to have minus pi over 6. And then we're also going to distribute the negative to our second term. So we're going to have a minus square root of 3. Whole thing is still negative. So we can distribute the negative. We would get root 3 plus pi over 6 minus pi over 2. And from here, we could find a common denominator and make it just one term, but that's not really the focus of this class. We're going to just leave it the way it is and focus on strictly the calculus part of class. So this is what we would register as our final answer. And there is no plus c, of course, because this is a definite integral. We have limits of integration, so there is no constant at the end. So I've decided to maybe wait until next class to dive into the trig substitution because it's something I want Nathan to be here for. So for the remainder of this class, we're going to continue on with this topic. We're going to continue on with using the trig identities to solve complex integrals. And then we're just going to be doing trig substitution on Sunday, assuming Nathan is here. So it's always a good idea to have a bit more practice. I want you guys to try one of these. I want you guys to try the integral of x times cosine squared of x. So let's take a look at the identity table and decide which identities might be useful to us in this situation. But before we even do that, I have a hunch that this might be an integration by parts problem because we have one thing times another thing. We have a clear u and a clear dv situation. But so before we even look at the identities, let's set this up as an integration by parts problem. So we have integral of u dv is uv minus the integral of v times du. We have a u is x, so then du is dx. We have a dv. dv is cosine squared of x dx. And then this is where things get a bit tricky. We have to find v, and the only way to find v is to integrate this function that we have assigned to dv. We have to integrate cosine squared of x. So let's see if we can think about maybe a few good strategies we can try for this one. Now, this is the point where we do want to look at our trig identity table. So I'd like for both of you guys to look at the table, maybe take a few minutes and glance through it. See if you can find any good identity we can use to rewrite cosine squared of x so that it is something to be integrated, something that's easy to integrate. So personally, I see a few of them that might work, but I want to hear if you guys have any suggestions. So take a minute and please type into the chat any identity you think might be useful. And it's okay if you can't find anything, just say you're not too sure if you can't find anything. I think we want to use one of the double angle formulas for this one. I think it would make things a bit easier. So we have cosine squared of x, and I'm going to write the identity on the board. There is an identity that tells us that 2 times cosine squared of x minus 1 is equal to cosine of 2x. And this is really helpful because we can integrate cosine of 2x really easily, but integrating cosine to the second power of x is not so easy. So we want to find a way to put it in terms of just cosine of 2x, because from there it's just a really simple U-substitution problem. So let's go ahead and solve for cosine squared of x. We want to add 1 to both sides, and then we want to divide everything by 2, which yields the following. There we go. This is going to help us quite a bit. So I'm going to replace dv. Instead of dv being cosine squared of x dx, I'm going to replace it and I'm going to make that into 1/2 cosine of 2x plus 1. So we still have to take the antiderivative of dv, but it's much, much easier now since we don't have a second power of the cosine function. We have just a single power function. Much, much easier to do. It's still going to be an integration by parts problem, though. We're still going to have to do uv minus integral of v du. We're going to have to plug in all of our values when we have them and then integrate. So I'd like for you guys to see if you can carry on the problem from here. See if you can find v, and then once you have v, just plug everything in and then integrate. So give it a try. I'm definitely here to help if you have any questions. But the more of these we do, the more comfortable we'll get. So give them a try, and please send me an answer if you get one. So our very next step would be to take dv and then use that to find v. So v is going to be a separate integral. V is going to be the integral of whatever dv happens to be. Oh, I forgot the dx. So v is going to be 1/2 the integral of cosine of 2x plus 1 dx. I don't need the parentheses there. So this is just a simple U-substitution problem. U is 2x, so then du is 2 times dx. I want to divide everything by 2. So that way we're going to have a 1/4 this time outside. We're going to have cosine of u plus 1 du. So the antiderivative of cosine is just going to be sine. Sine of u, sine of 2x, and then the antiderivative of 1, of course, is just going to be x. So this is v. We have found v. So now that we have that, we can substitute things in and solve the integral this time with what we're given. We have u times v, so that would be u is x, and then v is going to be 1/4 sine of 2x plus x. And then we have minus the integral of v times du. Du is just dx. So it's already looking much simpler and much easier. We can make this into x over 4 sine of 2x plus x squared over 4. And then it's another U-substitution problem. We're going to have the same u we had before. U is equal to 2x. Du is going to be 2 dx. So then 1/2 du is just going to be dx. So we have a 1/4 out front. We're going to combine that with the 1/2 from our du. We're going to make this into minus 1/8. Sine of u plus x dx. So the antiderivative of sine is going to be negative cosine. We already have a negative out front, so we're going to have a negative cosine, which is going to resolve to be a positive cosine. So it's going to be plus 1/8 positive cosine of u, which is 2x. And then the antiderivative of x is just going to be 1/2 x squared. And then this is an indefinite integral. We don't have any limits of integration, so there's definitely going to be a constant at the end. So our solution would be this. Bit of a tricky one. Good practice, though. We might have time for 1 or 2 more problems. I think I found a pretty good one for us to try. And by the way, this is being recorded, so you guys will be able to see this. You'll be able to review this video later on if you'd like, to review some of these concepts. So let's try to integrate a tangent to the 5th power of x times secant to the 4th power of x. And this is a definite integral. We're going to be integrating from 0 to pi over 3. So for this one, I want you guys to give this a try, but I will tell you what identities we want to use. We are going to want to use probably the Pythagorean identity. I'll give you a hint. We want to reduce tangent to a single power, and we want to have secant be a second power, and we don't really care about what the power of tangent is. Here, let's just write this. We want to have a secant to the 2nd power and a tangent to any power at all. I don't know how to write this. I would just say, I don't know. Here, I'll write it in English instead of math language. So we want to just think about real quick how we can get that. We want to think about how do we make the secant to just a 2nd power. We have a secant to the 4th power. We want to turn that into a secant to the 2nd power. So in order to do that, I think we're going to be wanting to use one of the Pythagorean identities. There is one that tells us that tangent squared of x plus 1 is secant squared of x. So that's the one we ultimately want to use. So we want to manipulate this somehow. We want to manipulate the integral somehow so that we have not a secant to the fourth power, but a secant to the second power. So I want you guys to try this on your own, but I want to at least tell you guys what the next step should be. We're going to leave the tangent alone, but we're going to split up the secant into a secant squared and then another secant squared. So now that we have that, we want to rewrite this using this Pythagorean identity and then integrate. We want to keep this one. We don't want to change this at all. We want to leave this as just secant squared of x. But we're willing to change whatever else is needed to be changed in order to make this into a simple U-substitution problem. So we have a few minutes left. I want you guys to see if you can finish this, and we will go over it briefly at the end in just a few minutes. A hint, use U-substitution. So there's not much time left, so let's just solve this together. So like I said before, we want to keep the secant squared of x because it is the derivative of another function, and we need to utilize that in order to successfully use U-substitution. But what we want to do is we want to make this right here in terms of just one function and not both of these. So let's replace this secant squared of x with tangent squared of x plus 1. And then if we distribute, we're going to get two separate integrals. We have integral 0 to pi over 3 of tangent to the fifth power times secant to the second power of x dx. And then the other integral would be tangent to the fifth power times tangent to the second. So overall, we're going to have a tangent to the seventh power times secant squared of x. And I'm sorry for keeping you guys late. If you guys need to leave at any time, no problem at all. But if you have time to stay, you can see how we finish this problem. Up to you if you want to stay or not. So we have something that looks really similar in both of our integrals. But let's get rid of some of this stuff. we can see that because they both have a tangent to some power and they both have a secant squared, we can actually use the same substitution on both of these. We're going to set u equal to tangent of x, and then we're going to set du to be secant squared of x dx. Works out really nicely. So in our first integral, we're going to have u to the 5th times du. Second integral, it's going to be u to the 7th du. So if we integrate the first integral we have, we're going to make this u to the 6th power divided by 6. U to the 6th power, that's just going to be tangent of x to the 6th. 0 to pi over 3. And then the next one is going to work really, it's going to work in a really similar way. We're going to have plus, this is going to turn into 1/8 u to the 8th power when we integrate. So it's no longer a calculus problem. All we have to do now is find the answer. So the answer to a definite integral is always going to be a number. So we want to start by finding what the tangent of pi over 3 is. So imagine the unit circle. That's going to be equivalent to a 60-degree angle. Tangent is going to be y over x. So this is going to be square root of 3 over 2. I think here. Let me just draw the unit circle real quick. Probably the ugliest unit circle I've ever drawn, but we're kind of running a little on time. So it is a 30, 60, 90. We have 1, we have square root of 3, and we have 2. So the tangent is going to be, I was right. It is square root of 3 over 2. So we have 1/6 times square root of 3 over 2 to the 6th power. And then we have minus tangent of 0 to the 6th power. And then tangent of 0 is going to be, well, tangent is x over y. No, sorry, y over x. So this would be 0 over 1, so 0 altogether. So the tangent of 0 is 0. Other integral is going to be the same thing, except to the 8th power and not to the 6th power. So the zeros just go away completely. We have 1 over 6. This is going to be 3 to the 3rd power, which is 27. This is going to be times 27. And then 2 to the 6th power is going to be 64. Plus 1/8. And then a square root of 3 to the 8th power is going to be the same thing as just 3 to the 6th power, which is going to be 27 times 27. 729. Huge number. And then 2 to the 8th power is going to be, well, we know 2 to the 4th power is 16, so 2 to the 8th is going to have to be 256. And then if you want, you could simplify. We could find a common denominator. We could combine them, but I think you guys have suffered enough with this problem, and I kept you late enough as it is. So if you guys don't have any questions, you're free to go. And keep an eye out on my YouTube channel if you'd like to review this video a little bit later. It should be up maybe by tomorrow, I'm thinking, tomorrow afternoon. So that's it for today. Enjoy the rest of your day, and I will see you on Sunday.